Welcome to This Is My Architecture at reInvent. We would like to share with you some of our This Is My Architecture videos and add some additional information regarding the architecture and the behind the scenes of these videos. Our first story is Nielsen's data out system that can process 55 terabytes of data using serverless technologies and AWS Lambda. Join Ofer Dubrovsky and myself for this great video and learn about this architecture and the massive scale it's processing. Welcome to This Is My Architecture. I'm Boaz, and I have here with me Ofer from Nielsen Marketing Cloud. Hi, Ofer.
Hi, Boaz.
Tell us about Nielsen Marketing Cloud.
So Nielsen Marketing Cloud is a data management platform. We prepare marketing segmentation data that can then be used for campaigns.
So basically, you're getting files from different resources and then sending them to the different networks.
Right. So we basically create all the data in another part of the system, and then my system, which is called Data Out, gets these files on this side and then processes them and uploads them to the ad networks that are partners of ours.
Okay, so let's walk through the system, what it does.
Okay, so I think the first thing I want to mention is that this system runs a huge amount of data. We process about 250 billion events a day.
That's a huge scale.
Right, and these events come in files. Each file has a bunch of events in them, which are the segmentation data. It gets processed and gets sent to the ad platforms. The files pretty much come into the system and are written to an S3 bucket. They get some processing like transformations and formatting using a Spark EMR cluster, get written to another S3 bucket, and from here they go to Lambda functions that do all the processing of last formatting and sending it to the ad platform.
So you have your process data and then you just taking it and splitting it with Lambda functions.
Yes, correct. So the Lambda functions actually do the last part of the work of uploading it to all the platforms. There's additional layer of data here, which is all the data about the files and how to manage them. So this information goes through here and gets written to a Postgres RDS database. We have a little work manager Lambda that reads the information, makes decisions which files need to process in which way, sends it to the Spark cluster. That gets written back to the database.
So all your metadata is basically stored in RDS and you keep updating it through the flow.
Correct. We have a second work manager, Lambda, that basically reads the information about the process files and then does like a fan-out architecture of invoking many Lambdas that then upload it to the networks. In total, we have over 100 networks we upload data to. Once these Lambdas are done, they update back through an SQS queue, and this gets updated back to the database.
Some status that I process this file.
Correct, and if it needs to be retried and stuff like that.
So this looks like a huge system, 250 billion requests per day. I assume you had some challenges with it.
Yeah, so I think the three things that are really interesting about the system are the following. One is scale, the other one is rate limiting, which is something surprising we didn't expect that we'd have to do. And the last one, which everybody's worried about always, is costs. Okay,
so obviously 250 billion events a day, scale is very important. Let's talk about the scale of the system.
Okay, so our top day ever, we had 55 terabytes of data. On that day, we got 17 million files. And we had about 30 million Lambda invocations.
This is one day.
Yeah, in one day. And the system basically managed it without any problems. We were constantly following it and just surprised at how well it worked. In some minutes, we had something around like 3,000 Lambdas up in the air concurrently running.
Okay.
The interesting thing about it is that on a normal day, the lowest hour in the day has about 1 terabyte of data, but the peak hours have about 6 terabytes of data. So the system has to breathe up and down as the data comes in and basically scale up and down throughout the day constantly.
Do you need to do anything to scale it up, scale it down?
This is really the nice thing about it. So because of the serverless Lambda function architecture, the system basically does it on its own. We just invoke a lot of Lambdas and it scales up. And as the data dwindles down, the amount of invocations go down. We pretty much get it for free.
Out of the box.
Yeah.
So I assume with 3,000 Lambdas invocated at the same time, rate limiting can be a challenge both internally and externally. Can you tell us about what you did to prevent those challenges?
So originally we didn't think that's an issue, but we got some emails from some of our partners that, guys, what are you doing? You're killing our servers. And we started checking, and obviously we could handle any burst of data that would come in. We'd automatically just handle it. But the world doesn't work like this. So some of the systems that you send so much data, it's kind of like running a DDoS attack against them. So we had to do something, and just to be good neighbors, and we introduced a rate limiting mechanism.
So this is a great opportunity to pause and talk about rate limiting. Rate limiting is something you have to take into account when building serverless applications, especially when your resources are basically unlimited and you can scale as much as you want. But this is not necessarily the case on the other side. And the system you're working with, if it's an API of a third-party vendor or a legacy system that might be running a mainframe behind the scenes or a database connection, can run out of resources when sending too much information. In Nielsen's case, they had to implement rate limiting to make sure they are not DDoSing their customers. And in your case, you have to take this into account when building your application, making sure you're not running out of connections if it's a database, API call, or any other system. Back to the video.
So the way it works is we have some smarts in this work manager Lambda. It basically invokes a lot of Lambda, so it needs to know about all of them. Yeah. So it makes some intelligent decisions based on the size of the files, the number of events in them, and so forth. And we could pretty much rate limit on anything we want that's really important to our partners.
Such as?
We can limit on megabits per second, the amount of HTTP connections open, number of requests, and a few other things like that.
And can you actually limit per specific network?
Yeah, so that's pretty much configured per network, and then we adhere to the limits that we set. So for example, if the limit, we have one network that we set a limit for 250 megabits per second. So if we get more data than that, it would just stay in the queue and wait, and then we'll just gradually send it out. The other interesting thing about it is that we had our own DDoS attack. So as the number of invocations of Lambdas grew, originally we were writing back to the Postgres database, but we ran into a limit of the number of connections you can open against the database, and starting to have it became a choke point. So we introduced another queue as a buffer that all the Lambdas report back to the queue, and we have one Lambda that picks it up in batches of events and writes it.
And you don't need it in real time, it can wait there.
Usually it's a few seconds, but it's fine. We just need an update if the file was successful or not.
So this is a great point. And we got a lot of questions regarding Nielsen's decision to go with an RDS database. Why they choose a relational database over, for example, DynamoDB, NoSQL, something that will be maybe faster and maybe give them some additional capabilities and works great with AWS Lambda. The main reason why Nielsen decided to go with the relational database is that in addition to storing information regarding the different transactions happening in the system, they're doing a lot of queries on this data. And the SQL query language allowed them to do complex queries and get a lot of information regarding the information inside this database. They're constantly checking for other alternatives, and they might change it in the future, but right now, this is the system they're using, and they are very happy with it. Let's go back and see the end of the video. Okay, so let's talk about cost. So I assume that size of a system, many of our customers are looking at it and say, this is probably pretty expensive.
Right. So I think the main thing we worried about as we were building the system is making sure we have costs under control. The system today costs us about $1,000 a day. So that's around $300,000 a year. And as we were building this, we really wanted to be in control of the costs. So we started measuring costs. So the way we measure it, we started out by the costs were about $7.7 per billion events. And we had a goal to reduce this. It took us about a year. Today we are at about $425 per billion events and still going.
So can you tell us a bit, how did you get from this 7.7 to 425?
Okay, so the nice thing about Lambdas, as opposed to other architecture where you're paying for the servers, and then if you improve your code, you're still paying for the servers. With Lambdas, the minute you improve your code and the Lambdas are more efficient, it immediately translates to cost savings. So we had a few initiatives to reduce costs. One of them, for example, is that we realized there's a trade-off between how long the Lambda function runs and the memory footprint. If you reduce the memory footprint, you save on the cost. You might increase the length of the time it runs, but it might still be worthwhile.
To find the exact point when it makes sense.
So it's kind of like an optimization problem. So we wrote a simulator that could simulate different loads on the Lambdas with different memory sizes. We experimented with it and run a few hundred different combinations and found the exact sweet spot of where it's going to be optimized, and then improved our code so it'll work exactly in that sweet spot, and that drove the cost down. Another thing we did is we played around with the number of HTTP connections that, or the requests we send in, in each connection, and we found that with the sweet spot there, that if we send more connections, we're waiting for all of them to complete, and it's going to take maybe longer, but the total cost may be lower because we're sending more data at the same time.
So we had a very interesting system here with a huge scale of 250 billion events per day. Rate limits that actually solved some of the problems you had during the implementation of the system, and of course the cost issue that you solve very nicely. Thank you very much, Ofer. Thank you very much for watching This Is My Architecture. Next is HSBC. This episode is about serverless security and banking, a combination really hard to imagine several years ago. And today this is the day-to-day operation of HSBC. Let's watch the next video.
Welcome to This Is My Architecture. Today we're talking about banking at scale with Ziniman from HSBC. What does HSBC do?
HSBC is one of the world's largest banks and is 7th in terms of market assets and capitalization.
Fantastic. Now you've solved some really interesting scale challenges with your architecture. Tell us about what you've solved here.
We have solved the primary problem of scaling. One of the biggest problems today about any institution is how they solve scaling. So when you usually deploy applications on-prem and suddenly you burst out, you run out of IP addresses and infrastructure. So what we have done is that we have created a smaller CIDR block and a larger CIDR block in 2 different VPCs. And one of the problems is that you could have created a simple VPC, gone to the network team and said, give me a IP range of 1,000 IPs. But guess what? You scale, you run out. And you scale again, you run out. So you have to draw a line. So how we have done it is that we went to the network team, got a smaller CIDR range, and applied that CIDR range to a set of proxies. And then we created a larger CIDR block, and then we scale out our lambdas within the larger VPC.
So you're running big scaled workloads here. You're running lots of lambdas, which obviously consume IP addresses. You're also running EMR clusters, Kinesis, a whole lot of things. How does the flow work?
Correct. So what happens is that in this we have created a /16 IP address ranging, which gives us 65,000 IP addresses. So any of the services that want to connect back to the bank actually talk through the private VPC endpoint that we have created. The private VPC endpoint connects to the proxies, and the proxies connect via direct connect back to the bank. This way they can all communicate back to the bank with segregation because you have a larger VPC separately.
So you've got the ability to deploy workloads but transit safely in and out of the bank's network environment.
Correct. And guess what? If we run out of 65,000 IP addresses, we create another VPC and connect it to the proxies. That way you could just scale out
just keep scaling and scaling.
Correct.
And what about on this side? You've got an interesting sort of similar pattern going on here.
That is very similar to what we have done here, but on the reverse side. What that enables us is that the proxies are actually controlled by a separate security team, and the security team whitelist all the domains that the proxies can talk to, which means the entire information flows from lambdas to the VPC endpoint, to the proxies, to the internet gateway, which talks out. A simple example of push notification that a service can then talk through that and goes out.
So you can apply this to many different patterns though that you might need to solve.
Another distinct advantage of this is that not every service right now has a VPC endpoint within AWS, but then you could implement this pattern to whitelist the AWS services you want on the proxies, which means you're still private and you're not connected to the internet.
So this has solved for the bank a number of challenges around scale and the ability to have really secure network access and separation of duties. But what else has it brought to the table?
What we have done with this is that in terms of deployments, we have 3 types of deployments through Terraform scripts and SAM templates. The first deployment, it configures the networks, does the CIDR blocks and all the plumbing work. The second Terraform script builds the infrastructure. And the third Terraform script deploys the code on top of the infrastructure. This is done through CI/CD. And it's actually built once, and then the code is promoted through the environments. But what this has brought to the table is that we can grow faster to markets wherever there's an AWS region. So if you want to go to that market, if there's an AWS region, we just deploy the scripts and it's up and running.
Just a few hours and you're good to go.
Brilliant, correct.
What a great solution. Thanks so much for sharing architecture with us today.
Welcome.
And thanks for watching This Is My Architecture.
Next is Temenos, building serverless banking software at scale. Join us for this great video.
Welcome to This Is My Architecture. I'm James, and I'm here with Tony Coleman from Temenos. Thanks for coming, Tony.
Hi James, glad to be here.
Can you tell me a bit about Temenos, Tony?
Temenos is the world's #1 banking software. We have around 3,000 firms, including 41 of the top 50 banks around the world, running the software and relying on Temenos to support the interactions and transactions of around 500 million banking customers.
That's quite a big deal. So tell me about some of the problems that you're faced with.
So there's two stories that we're going to talk about today, and the first one is around the idea of elastic scalability, automatic elastic scalability. This is some of the drivers we're seeing, very unpredictable workloads coming from the market, and we need a solution and an architecture that will support that. Not only to burst out when you see those peak loads, but as importantly, to scale back down so that you are only paying for the infrastructure that you need to service those requests. So that's the first part. The second part is ease of maintenance and manageability. And we're starting to hear phrases like lights out data center. A lot of challenger banks don't want an IT department. A huge part of the cost of an IT department is people. And by using and leveraging the platform and the managed services, a lot of that responsibility is pushed to the cloud platform.
Right, these can be hard problems to solve. So let's have a look at your architecture and see how you're doing that.
Sure. So all of our requests start and end at the API gateway, really. So it doesn't matter whether the request is coming from an open banking API or a customer on a mobile device or an assisted channel. It doesn't matter. Everything is routed through to the API gateway. Obviously, there are some perimeter services that we're not showing here. The API gateway will then, based on the endpoint, route one of two ways. The first route to talk about is this route on the left to Fargate. So here, the first port of call is the API gateway uses the Elastic Load Balancer, and this the load balancer's job here is to route the request through to the correct container image. So we use Fargate to host our containers, and that is where the transaction processing logic sits, and there we persist the data down into RDS. And then normally the response goes back up the chain. In addition, we have this stream along the bottom where we take the events that are generated as part of that transaction. Now that might be data events or it might be more complicated business events, but those are pushed through into Kinesis. We use Kinesis to push through those events in turn to a Lambda. And the Lambda's job here is to take that business event or the data event and produce a query optimized data model. And that's ultimately where the data ends up over here in Dynamo.
And so why are you using two databases here, RDS and DynamoDB?
So over in RDS, this is our OLTP database. It's designed and the database schema is there to process transactions as quickly and as efficiently as possible. Sometimes that means that the queries aren't as great as they might be. So we solve this by using a CQRS pattern and offloading the majority of our query workloads into a query optimized database. So not only is it a query optimized database, it's a query optimized data model. So not all the data ends up in Dynamo, only the things we need there.
This is a great example of using the right tool for the job, and in our specific case, the right database. From one hand, we have a SQL database running on RDS that is taking all the transactions and processing them as fast as efficient as possible. From the other end, we're taking a NoSQL database running on DynamoDB and storing only a portion of data on this database and using this database to run queries as fast as possible. And when you're running those queries, you're going to get great results and a great user experience. Let's watch the rest of the video.
Perfect. And then what's happening on this side of the diagram?
So for exactly that part of it, a lot, if not all of a query workload now gets pushed through from the API gateway directly to the Lambda. And the Lambda does the normal stuff that you'd expect to construct a query to the database, and then simply interrogates Dynamo to do that. And this gives us a very, very rapid response time. It gives us a very efficient footprint as well.
It's very nice. I mean, we can see that across the board here, you're using managed services, which must hugely reduce the amount of work your customers have to do.
Absolutely. And as an example of that, one of the deliverables of this architecture is a set of CloudFormation scripts. And these are being rolled out and used by customers and our engineers and pre-sales teams alike to spin up exactly this architecture, with very little skills or knowledge needed. So it's massively removing and reducing the need for manual steps in that deployment phase.
Brilliant. So you said the other challenge that you face is one of scalability and being able to elastically scale the system. Can you tell me more about how you're achieving that?
So it's a tale of two sides here. So the transaction processing engines, both in Fargate and in Lambdas, and the query engines in Lambdas as well, scale pretty much automatically for us. So in Fargate, we did some work to expose some custom metrics for the background services workloads. But for the online workloads, we use pretty much the standard metrics and the scalability of Fargate itself. Fargate's excellent because it enables us to not only scale out the containers, but it also scales the underlying infrastructure as well. This is important, obviously, for the burst out, but when the workload goes away, we scale back, so the infrastructure is not paid for anymore, meaning you're only paying for the usage that you actually need. So that's on the Fargate side.
That's very important. Now, you told me that you've been running a benchmark on this architecture. How's that going?
Very well. So it's, we are at the point now where we're talking overall the transaction load we're putting through is around 50,000 transactions a second. It's actually slightly higher. And that's a split between transaction processing happening and also the query workloads that we put through. But, over 12,500 transactions a second are what I would call proper transactions as opposed to queries, where there's a banking transactions, they're moving money, and it's pushing the, this sort of streaming technology. And it means that it was very important for us to test all of this out to ensure that the Kinesis streams and the Lambdas going into Dynamo was keeping up with the pressure that we applied to Fargate. And it keeps up with it very nicely. One of the things we were very surprised about, pleasantly surprised at these very high transaction volumes, is there was basically nothing we needed to do in the Lambda or even the Dynamo database model. Arguably, we got it right first time, but it was great to see that the Lambda and Dynamo just scaling when we were pushing it through to those extreme volumes with very little work at all.
That's fantastic, isn't it? Great to hear. Well, thank you for coming, Tony, and thank you for watching This Is My Architecture.
Whoa, 50,000 transactions a second. Another great example of building a serverless architecture at scale. Thank you very much for joining me today for This Is My Architecture to Reinvent, and see you in the next This Is My Architecture videos. Bye-bye.